Gravity is essential to defining orbits because gravity is what's pulling on something as it's going around something else. So, for example, the space station going around the Earth would just go off into space unless gravity pulled on it to pull it into a curved path like that. And so this is how you do orbits. In fact, what happens is you have to be going fast enough in order to stay in orbit. Orbits. He's able to describe how orbits work. And the idea is that you have a planet, okay, and then you have something in orbit. Well, what happens is it would move this way unless gravity pulls it down that way and moves down here. Now, if it's there, it would move this way, except gravity's pulling on it, so it ends up over here. And then now it would go straight, except that gravity pulls on it and pulls it this way. So what happens is that if you're in orbit, you're always falling towards the planet. You just are moving sideways so much that you miss. Your book has a kind of little graphic here that I've reproduced, which sort of shows this sort of thing. And that is, if you just drop an object, it falls straight down. If you move it to the side, it lands over here. If you throw it to the side really fast, it actually goes farther. So instead of hitting the ground here, because the Earth's surface is curved, it goes farther. Okay. If you throw it to the side so fast, as it's falling, the curvature of the Earth pulls away from it and it misses Earth and goes into a very elliptical orbit. Okay. If it's going really fast, then it actually keeps missing the Earth at constant height, and now it's in a circular orbit. And if it's going too fast, then it's not falling fast enough, and it ends up pulling away from Earth, and now it's in this big elliptical orbit like that. Now remember, you got the Earth, you got something orbiting Earth. If you are going too fast, then if you speed up, the orbit gets more elliptical. What if you slow down? That means you start falling closer to the Earth. And in fact, that's just how spacecraft re-enter Earth's atmosphere. For example, you have a spacecraft, the Dragon spacecraft that this past summer went to the International Space Station, and when it went up there, it had to go up and meet the space station in orbit, and so had to match the orbit exactly. But when it got ready to come back, what it did was it slowed down and let gravity pull it back to Earth, and when it got close enough, it started hitting the Earth's atmosphere. Remember, Earth's atmosphere is not like a sharp edge, it's a gas. When it hit the Earth's atmosphere, that slowed it down even more, and then that's how it came back towards Earth. Newton also revises Kepler's laws. He says, okay, p squared equals a cubed, but its total mass times p squared equals a cubed. So that means that the total mass measured in solar masses times p squared. P is the orbital time, and then a is the orbital distance. So that gives you the relationship. So it says we can revise that. So that means if you know the mass and solar masses, you can actually not just use this because, I mean, what's solar mass? That's the mass of the sun. So that's 1. The sun is 1 solar mass. So a planet going around the sun, m is 1, so this is just p squared equals a cubed. But if a planet's going, if a moon's going around a planet, then you put the mass of the planet in there. Now that turns out to be that is very important, because that means that we can redo the equation. M, okay, times p squared equals a cubed. So m is going to be equal to a cubed over p squared. Well, that means that if you can find out how far a moon is from a planet and how long it takes to go around, you can solve for the mass. Now that's total mass. That's the mass of the planet plus the mass of the moon. Well, the moon is so small, the mass of the planet plus the mass of the moon is basically the mass of the planet. So right away, once they figured out how far Jupiter's moons were orbiting away from Jupiter, they could plug into this equation right here, and now they know the mass of Jupiter. Jupiter has a mass that is about 1,000th of that of the Sun. And so this was a big discovery. They saw moons around Saturn shortly thereafter. And so that means in mid-1600s, they actually discovered, a fellow Christian Huygens discovered that there were moons around Saturn. So right away, they were able to measure the mass of Saturn. When they discovered the planet Uranus, they found moons around Uranus so they could find the mass of Uranus. In the mid-1800s, Asaph Hall discovers moons around Mars. So that means you could find the mass of Mars. Mercury and Venus have no moons. So we had no idea what the mass of those two planets were until we sent a spacecraft there, an artificial moon. We guess that Venus, because it's about the same size as Earth, had about the same mass as Earth. And that was a very good guess. It really did have almost the same mass as the Earth. Mercury is only a little bit bigger than our moon, and so we thought it would have a mass only a little bit more than the moon. We were wrong. Turns out Mercury has substantially more mass than the moon because it's got a much more dense core than our moon. And so this is how you measure masses in astronomy. It's not like you can take a planet, into the lab, put it on a balance and weigh it. This is how you measure it. Arthur C. Clarke, a science fiction writer, had an interesting idea. He says, well, p squared equals a cubed, okay, or total mass times p squared equals a cubed. So the bigger the a is, the bigger the p is. So he says if you had a satellite far enough away from the Earth, it would take 1 day to orbit. Earth is rotating once a day. So that means that satellite would look like it's hanging over one spot on Earth. That's how geosynchronous satellites work. And so that means that it just looks like it's hanging over that one spot. Now, it has to be hanging over the equator because the Earth rotates that way. So a geosynchronous satellite with a polar orbit would not stay in one spot. It would pass over the same spot on Earth at the same time every day, but it would not actually be a synchronous orbit. There are some military satellites that are set up so they orbit the Earth just like that, so they pass over the same spot every day at exactly the same time for surveillance purposes. There's another interesting thing here about these satellites. Okay, so we have the geosynchronous satellites here. If you're trying to move from one orbit to another orbit, so you have an orbit here, and the orbit here runs faster than an orbit farther away. The farther away the orbit is, the slower it runs. And so you put a spacecraft into orbit around the Earth, and you're going to tend to put it into a low orbit because you just barely get out of the Earth's atmosphere. Now you want to get to the big orbit. How do you do that? Well, one way would be just to power the spacecraft straight out to the new orbit. That turns out to be, if you go to the math, hugely energetic and actually require a rocket bigger than really makes sense. So there was a physicist named Walter Holman who proposed that if you're in a low orbit, that if you just speed up the orbit, then the orbit that will make a very elliptical orbit like that. And so what you do is at the top of the elliptical orbit, when it's going slow, you speed it up again to go into this other orbit. And we call that a Holman transfer orbit. And so now the interesting thing is that Walter Holman lived and died before the very first satellite was ever launched. The very first satellite was launched in 1957. So he came up with the mathematics of transferring from one orbit to the other before it was even possible to do. And in fact, this Holman transfer orbit is exactly how we do orbits. So this is how we actually measure orbits. And so this is in fact the way we do this. And so this is a very, very astute sort of thing that he came up with. Again, Kepler modified Kepler studied the motions here. Newton modified this by saying the total mass times p squared equals a cubed, which means just redo the math, and you can now solve for the total mass of something. And this is as I said, this is one of these major significant findings, because now we can start measuring masses.